Good morning, or well, almost afternoon. How are you all?
Doing good.
Good. Did you guys have a nice break? I know some of you didn't get a break, but if you did you have a nice break?
I had a good break from calculus.
Okay, excellent. We will wait just a couple of seconds before we start talking about anything. I had a good break too. I went to Chicago to see my son. It was awesome. All right. So we didn't have any homework over fall break. I did get your tests graded, but I haven't gotten them uploaded yet. I've got to go in and put down how much you made on each question inside my math lab. And I'll try to do that right after class so you can see your updated exam score. Now, remember, pardon me, I will drop one question from your overall score. So when you look at it, um, just so that you can see the total points on each question, I'll go ahead and enter all of those inside. Well, I don't know. You can see that also in Gradescope. So I may just enter the total grade in my math lab just to make it a little bit quicker so you can see your grades quicker. But the total points that you get on all the questions combined won't match up with the total points you have on your test because I drop your lowest score or your lowest question score. So that may be different, but I'll let you know exactly how I entered it when I get that done right after class. Does anybody have any questions in general before we get started with our new material? Really? Nothing, huh? Okay. There are only 6 of us in here. Huh. All right. So we are going to start something very different than what we've been doing in chapter 10. We're going to start talking about sequences and series, which really, I mean, sequences and series are some of the basics of mathematics in general. And so, one of the things that we're going to talk about first is just definitions of sequences and series and how they differ and how they're related to each other as well. So, we're going to start off by talking about the definition of a sequence. A sequence really is just an ordered set of numbers. So you might have, a lot of times we write it in subscript notation. The first, if this was the sequence AN, then the first term would be A1, the second term would be A2, A3, and so on and so forth. So one of the things that we can do is actually list out the terms of a sequence. More often for us, we have what we call explicit notation for sequences, where we write it as a function. So we might say A of n is equal to f of n. And in that case, when we write it as a function, this typically n is just going to be some subset of the non-negative integers. Maybe n is like 1, 2, 3, and so on and so forth. So we might say, for example, A of n is equal to 2n squared plus 3 over 5n plus 1. The n down here is the input. That's the term that you would be looking for. And we write it this way as opposed to f of n to differentiate between just an arbitrary function and the corresponding sequence. When you see it in this notation, you'll know that we're talking about a sequence so that the input is not going to be something like the square root of 7 or 45 fifth, 45 sevenths or something like that. It's going to have to be a subset of integers, non-negative integers. So for example, if I wanted to find a of 1 here, that just means I go to the function representation of my sequence and enter 1 for n. So a of 1 would be 2 times 1 squared plus 3 over 5 times 1 plus 1. So we would end up with 5 over 6 for the first term of that sequence. A of 2 would be 2 times 2 squared plus 3 over 5 times 2 plus 1. And so that would be 2 times 4 is 8 plus 3 is 11 over 11. The third term of this sequence. Just replacing the n's in our function notation with the subscript here. Remember, this is the place of our f of x. We're writing it in this notation to represent that it's a function of non-negative integers. So we're talking about a sequence rather than just an arbitrary function. So we would have, let's see, 9 times 2 is 18 plus 3 is 21 over 16. So if you're just, could you just go ahead and find like a of 10 if I asked you to? Of course you could. What would you do? You just go to your function and everywhere you see an n, you're going to replace it with, in this case, 10. So we would have 2 times 10 squared plus 3 over 5 times 10 plus 1, or we get 203 over 51. Now that's an explicit representation of the terms of a sequence. If we were writing it in bracket form, we would just have, 5, 6, 1, 21 over 16, 203 over 51, and so on and so forth. Another way that you can see the terms of a sequence is by a recurrence relation. And in a recurrence relation, terms of a sequence are defined in terms of predecessors. Pardon me. So you might have a of n plus 1 is some function of a of n. So for example, you might have something like, let's see. Well, thought I had one.
Does that say function of an?
It just says f of an. Are you talking about here?
Yes.
Yeah, it's f.
Okay.
So to represent a function, yes. Okay. I was trying to find a one in our homework that was a recurrence relation, but apparently my computer has frozen. Okay. Ah, here we go. So for example, we might say something like a of n plus 1 is equal to 5a of n, and they tell us that the first term is equal to 3. So this term and this term are separated by 1. So if this term is 3, then, or if this is, say, a of 1, then this would be a of 2. If this was a of 2, this would be a of 3, and so on and so forth. So if you wanted to write the first 4 terms of this sequence, well, we've got the first term, a of 2, which is a of 1 plus 1, just to write it in the form of this subscript, would be 5 times a of 1. Because if you're thinking about this as n plus 1, and the definition is a of n plus 1 is 5 times a of n. So in this case, this would be 5 times a of 1, or 15. Because a of 1 was 3. Sorry, I should have written that later. If you had a of 3, that is a of 2 plus 1. So that's 5 times a of 2. Why is it 5 times a of 2? Just because they told us so. Okay, and so this would be 5 times 15 or 75. And a of 4, which is a of 3 plus 1, would be 5 times a sub 3. So that would be 5 times 75. Okay, so that's what? 2 times 75 is 150, 300, 375.
Correct.
And that would be the first 4 terms of that sequence. Now, most of what we will do will have sequences involved that are expressed explicitly, but occasionally we will have an implicit or a recurrence relation. Sometimes they may just give you a few terms of the sequence. For example, what if they said that here are terms of a given sequence? Okay, so they just list it term-wise. Then they ask us to write the next 2 terms of the sequence. Now, writing the next 2 terms is all about recognizing a pattern. Okay, let's see about this pattern. If we think of all these as fractions, the numerators are all 1s, right? What can you tell me about all the denominators? Is there anything they have in common?
They're all divisible by 4.
They are all divisible by 4. And in fact, they're all powers of 4, right? This is 4 to the first power. This is 4 to the second power. This is 4 to the third power. 4 to the fourth power. Does this guy fit in line? Yeah, that's 4 to the 0 power. Okay, so if we're thinking about this as numerators being 1s and the denominators being powers of 4, the next term would be 1 over 4 to the 5th. All right. And what's 4 to the 5th? Well, let's think. 256 times 4,024. And the next term after that would be 1 over 4 to the 6th, which would be 1 over 4,096. Okay. Now, a lot of times these guys could be written several different ways. You just want to pick the simplest pattern that you see to rewrite that. We want to keep it as simple as possible. Okay, so what if I asked you to find a recurrence relation that generates this sequence? Now, once again, when I'm asking for a recurrence relation or an explicit formula, a lot of times there are several different possible correct answers. We just want to keep it as simple as possible. So our first term, and I'm going to call it a of 1. Technically, I could call it a of 0. But in this particular case, they told us in the statement of the problem, I just didn't write it down, but they told us that this guy starts with n equals 1 to infinity. Now, there's not a law that says you can't start with an a of 0 as far as sequence terms, but most of the time when we're talking about sequences, we're talking about counting the terms or listing the terms as a first term, second term, third term, which would indicate that starting with n equals 1 would be a good choice. And most of the time that will be true. But to be honest with you, when you're talking about sequences, in what we do with them a lot of time is we're trying to find a limit. And technically speaking, they won't even list this guy out here because really it's going to be the ending infinitely many terms that make the difference when we start talking about limits. So depending on the context, sometimes they'll tell you that it starts at n equals 1. Sometimes they will leave this part off and just tell you that it's a sequence of a of n. All right, so this is our sequence. I know my first term is 1. Why? Well, they wrote it that way. Okay. I want to write a recurrence relation. So I'm going to say, okay, a of n plus 1. What could I do to get from the first term to the second term with some, let's say, normal operation like multiplication, division, addition, or subtraction? Well, if I wanted to get from 1 to 1/4, one really easy way would be to multiply. So I could say that a of n plus 1 is 1/4 times a of n. Would that be true to get from first term to second term? Sure. Does that also get you from second term to third term? Well, if I multiply this term times 1/4, do I also get this one?
Yes.
Yep. Multiply this term times 1/4, I get this one, and so on and so forth. Since we're going with the denominator in increasing powers of 4, each time to get from one step to the next, you're multiplying by another 4 in the denominator, or the equivalent of multiplying the entire fraction by 1/4. So this would be an example of a recursive relation that would generate that sequence. As I mentioned, there may not be just one. We just want to keep it simple. We also want to find an explicit formula. Let me get rid of the shadow here. Hang on just one second. Maybe not get rid of the shadow, just move it. Okay, so we also want to find an explicit formula. For the sequence. And in the instructions, it says for the general nth term of the sequence. So in other words, I just want you to tell me how I could write a of n. Well, what if I just wrote it as 1/4 to the n? If I did that, what would a of 1 be?
The second term.
It would be the second term instead of the first term. And so what could I do to write it, just adjust it just a little bit to make that first term be a 1? Well, several different ways. We could say, okay, I could multiply that by 1/4, or I could say 4 to the n minus 1. If I do 4 to the n minus 1, when I replace n with 1, I have 1/4 to the 1 minus 1, or 1/4 to the 0, which is 1. My second term is 1/4 to the 2 minus 1, which is 1/4 to the first, which is 1/4, and so on and so forth. And so that would be a way, since I missed a term, I basically shifted my exponent. You could, however, write that as 1/4 times 1/4 to the n. In that particular case, though, well, actually, it would be 4 times 1/4 to the n, because that would skip 2 terms. If you wrote it as 4 times 1/4 to the n, would that also get it? Now, if n is 1, we've got 4/4, which is 1. When n is 2, we have 4/16, which is 1/4, and so on and so forth. But that's just kind of a fancy way to write 1/4 to the n minus 1. These guys are equivalent, just written a little bit differently. Which one's right? Well, they both are. Okay. So that part gets a little bit, I don't know, a little bit vague in that there are multiple ways that you could get a formula for a given sequence. So they'll typically be pretty specific on the computer about, which one they want. But as long as they're equivalent, you should be good. Okay. Now, a lot of what we will be doing involves limits of sequences. So let's think about what a limit meant to us. Okay, we've done limits in so many different places. When we're talking specifically about a sequence, if the terms of a sequence so I'm going to use A of n again. If they approach a unique number, as n increases without bound, so in other words, as n approaches infinity, we say the sequence converges to that number L. Okay. Or in our limit notation, we have the limit as n approaches infinity of A of n equals L. If the terms do not approach a particular number as n approaches infinity, we say the sequence diverges. Now, let's look, for example, at A of n equals, say, 1 over n. This sequence is part of the function f of x equals 1 over x. If you look at the function f of x equals 1 over x, I'm just going to look at the right half because for sequences, remember, our terms are always going to be, the subscript will always be positive or at least non-negative. All right. So this is what the right half of the graph of 1 over x looks like. If we're looking at f of n, the only difference is for the sequence part, we only have some of these terms. Specifically, we have the terms when n is equal to 1, n is equal to 2, n is equal to 3, 4, 5, all of the integer terms to the right of 0. So the terms of our sequence here would be this point, this point, this point, this point, so on and so forth, all the way out, continuing further and further. So can you tell me from things that we've done in the past, what the limit as x approaches infinity of 1 over x is?
0.
It's 0, right? That was one of our basic limits that we talked about. Of course, that was probably Cal 1. But when you're talking about the limit as x approaches infinity of 1 over x to a positive power, that's always going to be 0. This limit is 0. But these guys are just some of those terms. So if these as a whole are going to 0, what do you think is going to happen to the orange dots or the terms of the sequence?
Same thing.
It wouldn't have to follow along, right? Okay, its limit would also be 0. And in fact, in general, if f of n is equal to A of n, in other words, if this function is the function that corresponds to the terms of the explicit definition of the sequence, so if that's equal to A of n for positive n, and the limit as x approaches infinity of f of x is equal to L, then the limit as n approaches infinity of a of n is also equal to L. Why is that important? Well, what this tells us is if we can figure out what the corresponding function is, the overall function, and we can determine what the limit of that function is as x approaches positive infinity, then the limit of the sequence will be the same. They're going to converge to the same number. But if we're not looking at the overall function, a lot of the rules that we may have wanted to look at to evaluate limits might not work, specifically L'Hopital's rules. Because remember, to be able to use L'Hopital's rules, we had to be able to have differentiable functions at the top in the numerator and the denominator of our fractions. Whereas sequences are not going to be differentiable because they're a discretely determined function. They're never going to be connected, right? It's going to be a point for x equals 1, a point for x equals 2, and so on and so forth. But this gives us the fact that if the limit of the function exists, the limit of the corresponding sequence also exists. Big note. This only goes one way. It is not true in general that just because the limit as x approaches infinity of f of x does not exist, that the limit as n approaches infinity of a of n does not exist. So it goes one way, but not the other. If the corresponding function does have a limit as x approaches infinity, the sequence converges to the same number. But if the function fails to converge, that does not mean that the sequence fails to converge. For example, let's suppose we have a of n is equal to sine of pi n. Then the corresponding function from which these terms can be taken would be the sine of pi x. What does the graph of the sine of pi x look like? Well, it looks like the sine of x, except the period is changed. This graph, if you looked at the entire graph, you've just got your sine function, but you get one full period in 2 units because 2 pi over pi would be 2. So this would be 2, this would be 1, this would be 3, and so on and so forth. Okay. What can you tell me about the limit as x approaches infinity of the sine of pi x? Does it exist?
No.
It does not. Does it approach infinity? No, it just doesn't exist because of the infinitely oscillatory behavior. The y values for this function are oscillating between -1 and 1. And as we get closer and closer to, as x gets larger and larger, it's going to continue to do that. So this limit is just a does not exist. Okay, fine. That does not necessarily mean that the limit of this sequence does not exist. For the sequence, we'd have to go back and say, okay, the limit of the function doesn't exist, but we need to do some more investigating. What are the points on this sequence? Well, when you plug in n equals 1, you get the sine of pi, which is 0. When you plug in n equals 2, you get the sine of 2 pi, which is 0. N of equals 3, sine of 3 pi, which is also 0. So while this function does not converge as x approaches positive infinity, The sequence to which it corresponds here is comprised only of the terms that equal 0. All of these, this is just a really fancy way to write 0. Because remember, the sign of any integer multiple of pi is 0. So in this case, the limit as n approaches infinity of a of n, which is the limit as n approaches infinity of the sine of pi n, is just 0. Because in fact, all of those terms are identically 0. Okay, so it goes one way, but not the other. If the corresponding function does have a limit as x approaches infinity, then the sequence corresponds to that same number. But if the corresponding function does not have a limit as far as it doesn't exist, then you need to do some additional investigation about the corresponding sequence. But from the first part of this, that gives us a whole lot that we can do as far as laws for limits, or limit laws, I should say, for sequences. If we want to take the limit of a sum or difference, we can still take the sum or difference of the limits. If you want to factor a constant out front, we can still do that. Products, quotients, as long as the limit of the bottom is not 0, we're good. But the big thing it allows us to do is we can also use L'Hopital's rules. For example, if you wanted to say, what is the limit as n approaches infinity of this? Well, what would the corresponding function be? The corresponding function, overall function, would be 100x plus 5 over 6x. What did we do to take the limit as x approaches infinity of 100x plus 5 over 6x? Well, the limit of the top is approaching infinity. The limit of the bottom is approaching infinity. So we did one of two things. We had a couple methods by which we could evaluate this limit in Cal 1. We either looked at the degrees of the top and bottom. When they're the same, we get the quotient of the leading coefficients. But where that comes from is a direct application of L'Hopital's rules. This guy is going to infinity. This guy is going to infinity. From L'Hopital's rules, we can take that limit as the limit of the derivative of the top over the derivative of the bottom. So we would get that this limit is 50 over 3. That function is the overall function corresponding to this sequence. So if it converges to 50 over 3, then a of n also converges to 50 over 3. Okay. What do you think about this one? Does it converge or not?
The degree of the bottom is higher, so it should go to 0, right?
That is absolutely correct. Remember, if we're doing L'Hopital's rules, we'd have to go through 3 applications of it. Or we had the shortcut that we first learned in Cal 1 when we're talking about limits of rational functions. If the degree of the top is less than the degree of the bottom, that's always going to converge to 0. So this case, the limit as n approaches infinity of a of n would be 0. And the way we got it at first was we divided through by the highest power of n. At that time it was x, but n in the denominator, and we would get a 0 that way. Do y'all remember those shortcuts? When you have a rational function, So we've got a polynomial over a polynomial, like we do here. The limit as x approaches infinity of f of x is equal to 0 when the degree of the numerator is less than the degree of the denominator. The limit as x approaches infinity of f of x was equal to the quotient of the leading terms. When the degree of the numerator is equal to the degree of the denominator. And the limit as x approaches infinity of f of x is a does not exist. Typically, it'll be going to either plus infinity or negative infinity when the degree of the numerator is bigger than the degree of the denominator. Now, this is one case when you're talking about rational functions specifically. If the limit of the function is getting infinitely large, then the limit of the sequence will also be getting infinitely large. It's those where we're kind of hanging around close to 0 or something like that, or if we could have terms that could conceivably be consistent throughout, that you would have to go back and check. But if your original function, like if you do something in here and then we maybe go that way, if you take a sequence of terms along that graph, they will also be getting infinitely large. Okay. So does this look familiar to you guys? Have you done this shortcut before? Oh, hang on.
Maybe.
Maybe. Okay, but it does make it nice and pretty short as far as those are concerned, instead of having to go through L'Hopital's rules. So that'll give you a really quick answer to things like, okay, let's say we are asked to find whether this sequence converges or diverges. Think of it as a rational function. The degree of the top is 4. The degree of the bottom is 4. If we are actually going to use L'Hopital's rules, we need to look at the corresponding function so that we can talk about the derivative. But in this case, degrees of 4 in both numerator and denominator, you can say this converges to what in this case?
5/6.
5/6, and you're done. Okay. If you had something like, oh, this one, does it converge or diverge? And if it converges, what would it converge to?
It's gonna converge to 0.
Good. Because the degree of the top is less than the degree of the bottom. And when I say that this sequence converges to 0, another way that I could write that is the limit as n approaches infinity of that sequence terms is equal to 0. These two things mean the same thing. Okay, so we've done limits. Most recently, we did them as in improper integrals, but we haven't done a whole lot with L'Hopital's rules in a while, probably since, Cal 1. So let's look. What would you do if we had something like this? Oh, let's say our sequence is the arctangent of n squared plus 1 over n squared plus 3n plus 5. And we want to determine what's the limit as n approaches infinity of the arctangent of n squared plus 1 over n squared plus 3n plus 5. In other words, we're trying to determine, does that sequence converge or not? Well, let's take this bit by bit. Remember, limits will move inside of a continuous function, which if we looked at the corresponding f of x function, would be looking at the limit as x approaches infinity of the arctangent of x squared plus 1 over x squared plus 3x plus 5. So that would be the arctangent of the limit as x approaches infinity of x squared plus 1 over x squared plus 3x plus 5. What is that interior limit? Limit as x approaches infinity of x squared plus 1 over x squared plus 3x plus 5 is
1.
1. And what's the arctangent of 1? Remember, it's an angle between negative pi over 2 and pi over 2, whose tangent value is 1. What angle would that be?
Pi over 4.
Pi over 4. Good. Now, on the flip side of that, what if we had, say, b of n is equal to the arctangent of n squared plus 2? Here, if you take the limit as x approaches infinity of the arctangent of x squared plus 2, this part is going to infinity. Where does the arctangent, or what does the arctangent approach as its argument, or what you're taking the arctangent of, approaches infinity? In other words, what's that horizontal asymptote on the right for the arctangent function?
Pi over 2.
Pi over 2. Excellent. So the corresponding function approaches pi over 2. So the sequence would also converge to pi over 2. And so I didn't write it up here, I just wrote it there. The limit of this sequence would have been the same as the limit of that corresponding function. Okay. So remember, arctangents, we know what the horizontal asymptotes are. And in this case, since we're talking about sequences whose domains are subsets of the non-negative integers, we won't ever really be looking at x is going to negative infinity, right? We'll be looking at x is going positive infinity only. All right, any questions up to this point?
Could you flip back just one page? I think I'm a little confused on how when arctangent goes to infinity that automatically equals pi over 2.
We know that the arctangent function is the inverse of the tangent function.
That's right. You said asymptotes, right?
Right.
That's okay.
Yeah.
Gotcha.
Remember, the limit as x approaches infinity is just another, finding that limit is finding a horizontal asymptote on the right. And so if you're looking at that limit, that would just be the horizontal asymptote as x approaches positive infinity, which is to the right of that graph. And where those came from, remember, is negative pi over 2 and pi over 2 are the vertical asymptotes of the tangent function, which then become the horizontal asymptotes of the inverse tangent function.
Good deal. Thank you.
You bet. All right, so what about this one? I'm going to let you guys think about this just for a second. Any ideas? Does that sequence converge or not?
Does the radical and the power of 2 cancel out and make it like a power of 1, or not quite?
It does make it an effective power of 1, but you can't really cancel that out. But that's an excellent point. It is not true that this is equal to this. Those two things are not equal. So you can't just distribute that square root over that, but you're thinking along the right lines.
But the constant isn't really impacting all that much of it, isn't it?
It
So-
won't be. So your idea about that, as far as the limiting process, this really is an effective power of n to the first in the bottom. You just can't, like, just get rid of the square root. So with that in mind, what do you think we might do? Well, our corresponding function that we would be looking for the limit as x approaches infinity would be 3x over the square root of 16x squared plus 5. Now, if we start doing L'Hopital's rules on this, it may get a bit messy, okay? So I want to go back and look at the method that we first did these types of limits in Cal 1. What we did was we divided through by the highest power of x in the denominator. The highest power of x in the denominator is the square root of x squared, or the absolute value of x. Now, since x is approaching positive infinity, the absolute value of x and x are the same thing. So I'm going to divide everything through here by x. And we would get the limit as x approaches infinity of 3 over the square root of 16x squared plus 5 times 1 over x would just be over x. Now the question is, how can I deal with this? Well, in general, the square root of x squared is equal to the absolute value of x, as I just mentioned. But in this case, since we're going to infinity, this x is already positive, so this guy would be the square root of x squared. So we would have the limit as x approaches infinity of 3 over the square root of 16x squared plus 5 over x squared, which is the limit as x approaches infinity of 3 over the square root of 16x squared over x squared is 16 plus 5 over x squared. So this goes back to what you were mentioning earlier, that 5 is really not going to be adding a whole lot as x gets infinitely large, is it? So as x approaches infinity, this 3 is just stuck at 3, the 16 stuck at 16, but this 5 over x squared is going to 0. So we would end up with 3 over the square root of 16, or 3/4. Now, that is basically what we would have gotten if we thought of this as just being like a 16x there, isn't it?
Yeah.
Even though this isn't a rational function, it behaves very much like a rational function as x goes to positive infinity as far as the limit is concerned. We had to be careful with these when we were in Calculus 1 because we would get a different limit as we go to the right than for what we get as we go to negative infinity. But for us, for these guys, it's always going to be a positive infinity. So you actually can still use that idea about degrees of top and bottom, even when there's a square root there. Just recognize that if you rewrote this denominator as 4n plus the square root of 5, I'm going to count it all wrong because it just is wrong. But the effective degree here is the square root of n squared. So this guy down here is going to behave a whole lot like the square root of 16n squared for really big values of n, because these terms, I think it was Glenn, or whoever said that, this term is going to add very little to the size of the denominator. So as long as we're going to positive infinity, like if we had something like, oh, I should finish that statement though up there. This converges to 3/4 because that's what we got. If you had something, let's say we had, oh, this, if I asked you what the degree of the bottom is, it's 2. And even though this isn't a rational function, it's kind of a rational wannabe here. The leading power, the term that's going to take over that numerator is the square root of 25n to the 4th. And for positive values of n, that's 5n squared. So the effective leading term up here is 5n squared, and we have a 5n squared over a 4n squared down here. What do you think this converges to?
5/4.
5/4. You got it. Otherwise, you'll have to go through this whole process. Okay. Now, what about something that looks like this? So our sequence is a sequence of terms of the form 1 plus 2 over n to the nth. Well, let's see. If you take the limit as x approaches infinity of the corresponding function, as x approaches infinity, the 2 over x goes to 0. So the base goes to 1 and the exponent goes to infinity. Does anybody remember what we did with those in Calculus 1? We use L'Hopital's rules. Okay, but this was kind of the third level of L'Hopital in that we have to rewrite this twice, actually, because before we can apply L'Hopital's rules, we have to get the function back to a form that is either infinity over infinity or 0 over 0. Here, we don't even have anything over anything. We have something raised to a power. So to evaluate this limit, what we did was we said, okay, let's let this limit be y, okay? And I want you to consider the natural log of y would then be the limit as x approaches infinity of the natural log of 1 plus 2 over x to the x. Technically, it would be the natural log of that limit, but limits and natural limits move in and out of continuous functions. So we could say that the limit was on the outside. What would that allow us to do with that x right there? Where could we rewrite it?
As the coefficient of the natural log?
As the coefficient of the natural log. Good. So we could rewrite that as the limit as x approaches infinity of x times the natural log of 1 plus 2 over x. So now, as x approaches infinity, this guy goes to infinity. This guy goes to the natural log of 1, which is 0. So we've gone from something of the form 1 to the infinity back to infinity times 0. And now we're going to rewrite this as a quotient so that we'll have something of the form infinity over infinity or 0 over 0. So let's see. Most of the time, if I'm trying to rewrite a product as a quotient, if it involves a natural log there, I'm going to try to leave that alone. I'm not going to try to move that to the denominator because that derivative then gets really messy. So I'm going to rewrite this product as the natural log of 1 plus 2 over x over, all right, multiplying by x is the same thing as dividing by 1 over x. But now we have something of the form as x approaches infinity, this fraction goes to 0 and this fraction also goes to 0. And only when you have a fraction limit of a fraction of the form infinity over infinity or 0 over 0 can you then apply L'Hopital's rule. So I'm going to put an LH here to indicate that we're applying L'Hopital's rule at this time. And remember, what L'Hopital's rule tells us is the limit of this fraction, as in this case, x approaches infinity, will be the same as the limit of the derivative of the top over the derivative of the bottom. So I'm not taking the derivative of the overall fraction. I'm going to take the limit of the top function, and I'm going to take the derivative of the bottom function. The derivative of the natural log of anything is 1 over that thing times the derivative of that thing. The derivative of 1 is 0. The derivative of 2 over x, remember 2 over x is 2x to the minus 1. So that derivative would be negative 2x to the minus 2 or negative 2 over x squared. 1 over x is x to the minus 1. So the derivative of that bottom function is the derivative of x to the minus 1, which is negative 1x to the minus 2 or negative 1 over x squared. And here's what you have to be careful about. If we just went with infinity here, this would be going to 0, this would be going to 0, and we appear to be kind of stuck. But before you apply L'Hopital's rules again, what you want to do is make sure that you do any simplification that you can. For example, if you multiplied or invert and multiply by this fraction, we'd be multiplying by negative x squared over 1. So that x squared and that x squared would cancel, and we would be left with the limit as x approaches infinity of negative negative makes positive 2 over 1 plus 2 over x. And as x approaches infinity, this term approaches 0. So we have something approaching 2 over 1 plus 0, which is 2. Now, is that the answer to the original problem? No. That is the natural log of what we were looking for. We were looking for y. This is the natural log of y. So we have the natural log of y is equal to 2, which would mean that y equals e squared. Or this function corresponds to e squared, so its corresponding series also converges to e squared. So in section 10.2 specifically, we will be taking limits of things similar to what we did in Calculus 1 in a slightly different context, because now we're actually looking for the limits of corresponding sequences to the given functions or to a particular function. But L'Hopital's rules can be used. Questions before we take a break? And don't worry, we will do another one similar to this when we get back. All right, so let's pick back up at 105. Quick break. All right. So what if we had, well, maybe, this. So it's something similar to the one that we just did. But if we are looking at the corresponding function and trying to take the limit as x approaches infinity of the corresponding function here would be 1 minus 4 over x to the 2x. So I'm going to just call this y because we're going to be doing a similar process. As x approaches infinity, what's inside the parentheses approaches 1, and what's outside the parentheses approaches infinity. So we're going to once again consider the natural log of y would be the limit as x approaches infinity of the natural log of 1 minus 4 over x to the 2x. Using our laws of logarithms, that would give us the limit as x approaches infinity of 2x times the natural log of 1 minus 4 over x. Okay, so we've gone from something of the form 1 to the infinity to now this part goes to infinity. This part goes to the natural log of 1, which is 0. So we'll take one more step back and rewrite it as a quotient. And we'll have the limit as x approaches infinity of the natural log of 1 minus 4 over x all over the reciprocal of 2x is 1 over 2x. So at this point, as x approaches infinity, this guy goes to 0, and this part goes to 0, so this is approaching the natural log of 1, which is also 0. So we have something of form 0 over 0, at which point we can actually apply L'Hopital's rules, and we'll have the limit as x approaches infinity of the derivative of the natural log of a function is 1 over that function times the derivative of that function. Now remember, 4 over x, or I should say negative 4 over x is negative 4x to the minus 1. And so the derivative of negative 4x to the minus 1 is positive 4x to the minus 2, or that would be 4 over x squared. And that will be divided by, this is 1/2 times x to the negative 1. So the derivative of that will be negative 1/2 x to the negative 2, or negative 1 over 2x squared. And just like with the last one, we don't want to keep going here and apply L'Hopital again without trying to simplify first. And if we do the same type of simplification as we did last time, this x squared and this x squared will cancel. And so, because what happens is when you invert and multiply, you're actually multiplying this by the negative of 2x squared over 1, or 2x squared over negative 1. So that x squared and that x squared cancel, and we have the limit as x approaches infinity of 4 times 2 is 8 over 1 minus 4 over x times negative 1. And as x approaches infinity, this guy goes to 0. So in the denominator, we have a 1 minus 0 times a negative 1. So this is approaching 8 over negative 1 which is -8. But that, remember, was the natural log of y. We were looking for y. If the natural log of y is equal to -8, then y would be e to the -8. Since the corresponding function converges to e to the -8, the sequence would also converge to e to the -8. Questions? Sorry, I know you can't see that whole thing right there. Any questions? All right, if you are here right now, you have 30 seconds to say I'm here.
I have a quick question about where that 2 goes. Whenever you have the 2x squared and it cancels out the x squared, where does
I multiplied the 2 times the 4 and got 8.
oh, that's it. Okay. Thank you.
No problem. All right. So do you guys see anything kind of maybe a pattern here going on? Notice here we got an e squared. Here we got an e to the -8, but there was a 2 there. So this sequence could be written as 1 minus 4 over n to the n all squared. If I asked you to look at those for a minute and then just guess based on any kind of pattern you might see here. If I wrote the sequence as 1 plus 3 over n to the n, and I asked you what that converges to, what would you guess that it was going to be?
E to the 3rd.
That is absolutely correct. Notice if this was just a constant c. Okay, so I'm going back to this one just for a second. If this was a c here, like a 3 or a 5 or a -2 or anything like that, all of this stuff would be doing exactly the same, except where I have a 2, I would have a c. So when we ended up, we'd end up with an e to the c. So you can either go through this L'Hopital's rule every single time, or you can use the fact that the limit as x approaches infinity of 1 plus a constant over x to the x is just going to be e to the c. And I won't begrudge you using this fact. It's a limit that they give you in this section of the text. We went through a couple, brute force, but you'll always get that. So if you had something like a sequence of the form this, you could think of that as 1 plus 2 over n to the nth, all raised to the 3rd. Because remember, when you take a power to a power, you multiply the exponents. So as n approaches infinity, this part approaches e to the 2nd, and then that's all cubed, and you will get e to the 6th. Which is awfully nice to be able to do it that way instead of having to go through and do L'Hopital's rule. Yeah?
Yeah.
All right. Couple more things that I'd like to mention, at least briefly. And we'll do more with this as we go on into later sections. But are you familiar with factorials? If you've had a statistics class, you've probably seen those where if you've done combinations, permutations, that kind of thing. But we will deal with factorials a bit as we go forward. So, and there's, I think, one problem in this section where you're dealing with it. But what you want to know is factorial, in factorial for us is defined for 0, 1, 2, 3, 4, and so on and so forth, non-negative integers. By definition, 0 factorial is 1, and 1 factorial is also 1. In general, n factorial is n times n minus 1 times n minus 2 all the way down to 3 times 2 times 1. So for example, 5 factorial would be 5 times 4 times 3 all the way down to 1. So that's 120. Okay.
So why is 0 factorial equal to 1 factorial?
It's by definition.
It's just something they said.
It is, well, it is a definition. So,
Okay.
you know, yeah. And there's a lot that goes into it. We're just not quite there yet, as far as you can actually extend the idea of factorials to include other inputs and things like that. But the only ones that we'll deal with are the non-negative integers. Excuse me. One thing you want to keep in mind is that, you know, when we were talking about how quickly, or if we're talking about how quickly functions grow for larger values of the input, you know, things like x squared, x cubed, x to the fifth, those approach positive infinity as x approaches infinity. Things that get there faster are things like exponential functions. They approach infinity faster than your polynomial functions. And of course, that, I mean, as x approaches infinity. Factorials go to infinity much more quickly than even exponential functions. In fact, you know, let's see, I got a TI calculator here. If you take, let's say, I can't ever remember exactly where it falls apart. But if you go to, it does help when my calculator is not, is one where I can actually see everything, because it's not, part of the lines are missing. Okay, so if I go to my factorial here, if I do 75 factorial, it's already telling me I have just fried my calculator. So I can't put in even 75 for a factorial because the number is so large that my calculator can't deal with it. Let's see, will 50 work? Doesn't mean that it doesn't exist. It's just too big for our calculators to handle. Yeah, 50 will work. We get about 3.04 to the times 10 to the 64th power. So for relatively small inputs, factorial gets huge. It grows more quickly than anything that we've done before. Okay, and in fact, there's only going to be one function that we talk about that grows more quickly than n factorial, and that's n to the n. It goes to infinity even more quickly than n factorial, because, you know, n factorial is n times n minus 1 down to 1, but n to the nth would be n times n, that same number of factors. So it's bigger even than the factorial is. But why does that matter? Well, for one thing, we're going to need to be able to manipulate factorials, do cancellations and things like that with them. And we are also going to be very interested in how quickly functions get bigger. Because when we start talking about series, which we will do, well, we might mention them later today, but we'll really start talking about series on Monday. Series are very dependent on how quickly the size of the terms get smaller. Because in a nutshell, what we're doing with an infinite series is we're adding up all the terms of an infinite sequence and asking the question, do we get a finite answer or an infinite answer? Well, if you're adding up infinitely many terms, then and getting a finite answer, realistically, the terms are going to have to be getting smaller and smaller. So if you're looking at terms of a sequence, we want to know, is the top getting bigger faster than the bottom, or vice versa, or what's going on? And so how quickly different types of functions get bigger matters, okay? But in this section, the only thing that you might be doing with a factorial is doing some cancellation. So let's look at how might you cancel a factorial like this. Let's say this is my terms of my sequence. And I asked you, does that converge or diverge? Well, we can't use L'Hopital's rules on factorials because it's a discretely defined function, and I can't take a derivative of n factorial. So we'll have to do something else. In these guys, if you want to know whether it converges or diverges, what you want to do is simplify the fraction. Okay. N factorial, remember, is n times n minus 1 times n minus 2 all the way down to 1. N plus 1 factorial starts with n plus 1, then we subtract 1 and we would get n, subtract another one, we'd get n minus 1, n minus 2, all the way down to 1. So canceling, these terms would all cancel with these terms, and we would be left with just 1 over n plus 1. This fraction is a really fancy way to write 1 over n plus 1. But those two are indeed equal. So the limit as n approaches infinity of a of n would be the limit as n approaches infinity of 1 over n plus 1, which is
0.
0. So we would say that this converges to 0. Okay. But you have to know what the factorials mean before you know how they cancel. Okay. So what if you had something like b of n is equal to 2n minus 1 factorial over 2n plus 1 factorial. And I just asked you to simplify the fraction. Okay, 2n minus 1 factorial starts with 2n minus 1. The next term down would be 2n minus 1, which is 2n minus 2. We go 2n minus 3 all the way down to 1. 2n plus 1 factorial, however, would start with 2n plus 1. What would be the next term down?
2n.
2n, good. And then 2n minus 1, 2n minus 2, all the way down to 1. So this factor cancels, this factor cancels, this one would cancel all the way down to the 1, but these two guys are left hanging out. So that fraction would simplify to 1 over 2n plus 1 times 2n. Now, if instead I asked you, does that converge, what would you tell me? What does
It converges to 0.
it converges to 0, because remember, we've done these before. The degree of the top is 0, the degree of the bottom is 2. This converges to 0. But as I mentioned, we'll do a lot more with factorials later, but there is one problem in this section that they bring it in, but you'll just have to simplify the fraction. Now, one more reminder about a limiting process that we may not have used in a while. What if I gave you something like this? And I asked you to find that limit or to determine, does it converge or does it diverge? Well, if we look at the limit of the corresponding function, that would be sine x over x squared. Does anybody remember what we used to find those limits? But the problem is, see, the limit as x approaches infinity of sine x just doesn't exist because sine x, remember, is oscillating between -1 and 1 all the time. And x squared is getting infinitely large. What did we do? Ever heard of the squeeze theorem? I know you have. What is sine x always between?
-1 and 1.
-1 and 1. It is true that -1 is less than or equal to sine x, and sine x is less than or equal to +1. And so -1 over x squared will be less than or equal to sine x over x squared will be less than or equal to 1 over x squared as x approaches infinity. Okay? Because as x approaches infinity, these denominators are really big positive numbers. And what the squeeze theorem allowed us to do is if this function is squeezed between these two functions, if we can take the limit as x approaches infinity of -1 over x squared, and we can take the limit as x approaches infinity of +1 over x squared, if those are equal, then the limit of the function in between those two will have the same limit. What's the limit as x approaches infinity of -1 over x squared? It's 0. What's the limit as x approaches infinity of +1 over x squared? It's also 0. Since these two guys are both going to 0, and this function is between those two, then by the squeeze theorem, the limit as x approaches infinity of sine x over x squared is also 0. So this sequence converges to 0 because its corresponding function converged to 0 as x approached infinity. And so those were kind of common when we had particularly a numerator that was like a sine or a cosine or maybe even arctangent, those that we can squeeze between, nice constants. Sine and cosine can both be squeezed between -1 and 1. Arctangent could be squeezed between -π/2 and π/2. So really most of what we've done today as far as limiting is concerned is kind of a review of the limiting techniques that you used in Calculus 1, but for a slightly different purpose. All right, questions? All right, I kind of toyed with the idea of going ahead and starting section 10.3, but I think I want you to concentrate on getting these two sections done, and then we will talk about adding up the terms of sequences, in other words, series, starting on Monday. Any questions?
No questions here.
All right. Well, oddly enough, unless you do have some questions, if you do have anything you want to stay back and chat about, feel free to do so. Otherwise, enjoy your, I guess, next 20 minutes that I didn't really mean to give you. But okay, I will talk to you on Monday. Have a great weekend. And I'll go ahead and get your test grades up within as quickly as I can after we get done here. Have a good one.
Thank you,
Thanks for-
Professor. Have a good day.
Bye.
Yep. Bye.